Hello, good evening, everyone. Gonna do a couple of talks tonight. First one of which is going to be how to parse a file. We'll talk a little bit about Kotlin later as well. So this is a talk I've done a couple of times. It's a bit of a little bit of a war stories kind of talk, stuff which I've done in worked with, and it's a little bit back to basics on how to work with sort of parsing and things like that. And the idea really is to look at how you go about parsing a file. I'm going to start very, very simply. A little bit of advice, really nice advice. Don't bother. There's no need. Generally speaking, you don't need to write a parser. You can just use an off-the-shelf package to read some data and work with that data. Unless it's your company's core competency to work with parsers and work with specific file formats, don't. Just use an XML, use JSON, use YAML, use what? Actually, don't use YAML. YAML's horrible, so we'll skip that one. And in fact, JSON is basically just XML, so you can. Anyway, that makes for a very short talk, so we will instead, I think there's a couple of different reasons of why you'd actually want to write a parser, really. First of all, really, is things like sort of speed or efficiency. So if the off-the-shelf package you're using doesn't fit your needs, so perhaps you've got massive files where the general-purpose parser doesn't work terribly well with it, or perhaps you've got thousands and thousands of little files where, again, general purpose one doesn't work with that. It's allocating too much memory, it's taking too long, performance reasons, and so on. But with all of these now, you kind of got to take the trade-off into account. So, yes, you might want to be able to, to reduce your dependencies, improve your speed and efficiency, but there's a cost associated with that, and that you are then taking on the maintenance of a parser. And you've got to make sure that it is correct, that it is working, that it's secure, that it's performance, that it's all that. So you are now sort of allocating resources to a parser which you perhaps don't necessarily need to maintain. Let somebody else do it for you. So another good reason would be to reduce dependencies. If you're in a constrained environment, if you're on console or mobiles, for example, you might not want to bring in another assembly. You might want to just use your own simple file format, simple parsing. You might just have a custom or simple file format. So it might be very easy for you to just kind of pull those files in and read them. But again, maybe it's actually better if you just put them into as JSON files. Maybe that's going to be easier for you altogether. Another good reason would be for like a domain-specific language. So if you need to parse something which is domain-specific, something like a make file, something like HTTP headers, or standard out from another file. Although if it's standard out from another file, that's usually going to be some sort of command line script that you want to use, and it's probably quite simple and throwaway and not so much of a structured parser that we're going to be sort of talking about here. HTTP headers, there's probably going to be libraries already out there to do it for you. Other things you could do, though, are things like natural language commands. So, if you use Slack, you can use the / command, /remind me at 10 o'clock tomorrow to whatever. That's where it could be useful. The other reason, though, is kind of where I come in, and that's when the structure of the file is as important as the contents itself. So this is me. Hello, I'm Matt. This is what I look like on the internet. I ought to change that, but it's cute. And I work for JetBrains. I'm a developer advocate. I work for JetBrains. I work with the sort of .NET tooling there, with ReSharper, with Rider, and so on. And if you don't know JetBrains, JetBrains builds IDEs. JetBrains builds IDEs for basically any language you can throw a stick at. And the way they work is very, very similar. And if you drew the architecture of a JetBrains IDE on the back of a napkin, you'd kind of roughly get something like this. At the very bottom, you've got the sort of the core platform, the base platform, the simple things like UI stuff for file handling and so on. Next level up, then you've got things like a project model, so you know what files you're working on. And then above that, then, is the really important layer, this thing called the PSI. This is one of those acronyms that we've kind of forgotten what it actually means. I think it's Program Structure Index. It might be interface, whatever. And that's really, really important, because that's the thing which gets all the information about all your files. It indexes everything. It builds a big index on all of your files and all of the words that are used in your files, or the structure of your files, and how they relate together. And it's from this that we can then build features on top of things. So if you want to do navigation, we just look something up in the PSI index. If you want to do refactorings, we just use the PSI to manipulate the code that you've already got. If you want to do any kind of things like recognize unit tests or inspections and things like that, we can walk the syntax trees that we've got of the PSI. So basically, once you've got a PSI, you can do a whole ton of things. So that's the big thing up here, features. We've got loads and loads of features. and they're built upon this index, this framework here, this PSI. It's a bit of a double-edged sword, because if we want to build anything, we have to then build a PSI for a particular language, and so that's quite an investment up front. So if you want to add a new language, there's a lot you've got to do to add a new language, and then you can start building features. But once you've got that, you can do tons and tons of things. By the way, if anybody has any questions at any point, please just shout out.
Can I answer?
Yes, of course.
In the PSI, do you have some kind of context awareness that allows it to choose components of the PSI that are appropriate to the particular language context? So to promote usability, reusability between your different IDEs, or is it really built specifically per IDE?
I'm not quite following.
So the PSI that you have there, is that common across the IDEs?
Right.
Or is it unique to each IDE?
Okay, yeah, so is the PSI common to all IDEs, or is it unique per IDE? Yeah. The answer is a bit of both.
Right.
So there are common structures, common features, common language, common sort of interfaces, for example, and then particular languages will build on top of those. So, for example, in the IntelliJ side of things, IntelliJ is Java and WebStorm and PHP and RubyMine and all those kinds of things. There are common Java-based, JVM-based interfaces which everything builds on to do stuff. In ReSharper and Rider for the C# and .NET world, obviously you can't reuse the JVM stuff, but then there's a very similar set of interfaces and helper methods to doing that, for working with that. And there are helper methods there for things like low-level refactoring of trees, of the syntax trees, and moving things around and working with that. So yes, there's a certain amount of common functionality. So you can almost imagine that split in half and sort of utility functions, and then a whole load of boxes across the top here then for each particular language.
Yeah, that's what I was going.
Cool. Right. So where do I come into this? I've been working on the Unity support for Rider. So Unity is games engine, and it's a lot of fun. There's a lot of things there, and it's surprisingly massive. If you haven't heard of Unity before, there's like millions of people using it. If you've got a mobile phone with any game on it, chances are that game is built in Unity, and it's very popular and it's cool. And we can do a whole bunch of things with the C# side of stuff, but there are other files that Unity uses, one of which is a shader file, and the shader file allows you to do cool things with the GPU. And that's roughly where my knowledge of what the shader file thing does, but I know all about the file format and how to work with it. I wanted to add support for this into Rider. I wanted to have syntax highlighting, code folding, autocomplete, syntax error highlighting, inspections, all this kind of stuff in there, so I wanted to build that. And if you remember with the diagram, that meant I had to build a PSI level. So that means I had to parse this file and work with it. So what am I trying to build? A syntax tree, something like this. So it doesn't matter if you can't quite see this, it's too small and everything, but this is the idea. We've got this whole syntax tree which is describing the shape and the structure of the file that's there. And we'll have a bit more look into that as we go along. So this talk is a little bit about, as I say, it's a bit war stories kind of thing, and the focus is not just how to parse a file. It's me coming from a particular point of view, how to parse a structured file for an IDE. And the IDE imposes a certain set of constraints that are unique to an IDE, which make it a lot more fun and interesting. So how do we do it? How do we parse a file? Here's my straw man. This is the very, very naive parser. You read a character, you match a character, you read a character, you match a character, you read a character, you don't match it, oh, there's a syntax error, it goes on. This will work, but it's obviously very, very naive, and it is not maintainable, and it's horrible, basically. This is tells you roughly what's going on, but you need to split out the responsibilities. And basically, someone's already done this for us. This is old news. There's three main responsibilities that you want to do when you're parsing a file. You want to read the individual characters that make up the sort of different tokens that are that define the file. So things like keywords, identifiers, the punctuation, the brackets and the commas and so on. You then want to be able to recognize the complex constructs of putting all these together. So keywords together with an identifier means that you've got a variable declaration and so on. And then you want to act on the complete construct so that when you've built this construct, you know what to do with it, you can do a thing. And that can be, that's going to be sort of domain specific. So you might want to just write stuff out to the outputs, you might want to process it, you might want to in my case, build a PSI tree, a syntax tree, which we can work on, build semantic models on top of it so that we can index stuff and navigate and so on. And somebody's already done this work. It is old news, and this is basically what a compiler does. So, this is like the structure that you're going to get from the Dragon book on compilers from 1977. This is old hat. And it's the first three on the right side, on the left side there, sorry, which are the important things: lexical analysis, syntactic analysis, and then semantic analysis. Or to put it a little bit simpler, lexer, parser, and then a result, something you can work with, something you can then process and do some stuff with. So, lexers, what do we mean by a lexer? What is a lexer? So, it's also called a scanner. So, if ever you're sort of working in this area, you might see it called a scanner. And it performs lexical analysis, which doesn't really help much. But that's all to do with vocabulary. It's all to do with matching characters into words, into tokens, into useful things. Rather than having just like a stream of characters that you have to do something with, you can convert it into a stream of tokens. And then you can start to work with those tokens to recognize what it is. So having a stream of characters, a big long stream of characters, is really hard to work with. But if you've got a var keyword, an identifier, an equals, and a number, and a semicolon, you can recognize that as an expression. And so yes, we convert this into a stream of tokens, and the token will represent things like identifiers, comments, string literals, the punctuation, and so on. One of the key things about this is that the tokens are lightweight. They are very usually very cheap to create and to use, and typically they are integer values. So it's very easy then to sort of compare and work with and match against it to recognize the complex constructs. In ReSharper, because the Unity stuff is built on top of ReSharper, and ReSharper is part of Rider, these are actually singleton object instances, but that just means we've got functions which we can use to work with those. And then the parser works with this stream of tokens to recognize the bigger constructs. And again, because we're just using integers, that's really cheap. You're just comparing numbers. And if it's a whole bunch of numbers in a particular stream, you recognize that as an expression. And again, with ReSharper being object instances, those are also very cheap. Comparing object references is also cheap. One of the interesting things, though, is that a lexer can often be the hardest part to write, because you've got to convert this big, long stream of text into a whole bunch of tokens. And so you've got to recognize the keywords, you've got to recognize the identifiers and the punctuation and so on. Whereas the parser itself is just like, do I have an identifier? Do I have a keyword? Do I have an equal sign? And so on. Much easier. So what does it look like? Well, on the left here is an example of one of my shader files. It's a fairly sort of structured file there. It's got some comments. It's got a keyword and an identifier, open and close brackets and chunks inside there. This is what you get as the output from a lexer there. It's a stream of tokens. And the tokens can be different lengths. They can be different types. And it gives you an offset, and the offsets between the tokens gives you the length and so on. And I've got things like end of line comment, a new line, a keyword, whitespace, string literals, new line, load braces. So it's very detailed and very simple. The good news is lexers are a bit of a solved problem. People have already worked on this, and there's generally just more or less one way of doing this. And the idea is that you use a lexer generator, and these lexer generators have been around for a long, long time. So probably the first one there is Lex, which is nearly as old as I am, but not quite. And that has then sort of evolved into Flex, which does pretty much the same sort of thing, but is probably GNU-based or something. You know what the open source world is like. And these have then been ported to different languages as well. So you've got CSLex for C#, FSLex for F#, JFlex if you're in the Java world, and so on and so on and so on. There's pretty much a lexer generator for every language that you want to work with.
So can I ask a
Yes.
clarifying question? Because you said earlier that you've kind of got a special case where it might not solely, because you're working in an IDE, it might not solely be that all of the lexical analysis works because people type things incorrectly.
Right, yes, that's a very good point. So the question being that the IDE imposes a certain set of constraints, and therefore that might cause problems for lexing and parsing. And the answer is yes, it does, and I'll come on to that.
Right.
I'll come on to that. But generally speaking, it's not as bad as you think.
Okay.
It is, but it's not. For lexing, it's generally not, because you just recognize tokens.
Right.
And you recognize a token, and those tokens can be in any order. They can be incorrect, they can be wrong, they can be anything, but the Lexa will recognize tokens. And it'll spit out a stream of tokens, and it's up to the parser to try and make sense out of them. But we'll come back to that, definitely. All right, so because these Lexa generators are all pretty much based on the same idea, they're all fairly sort of standard file formats. They're usually sort of split into three sections. You've got like a user code block where you put in things like using statements of the code that you want to use. You have a second block sort of separated by the $% sign, and in here you can put in directives, which tells the Lexa generator how to generate things differently. You can declare regular expression macros to match your code, to match the input stream that's coming in with the characters. And you also get to declare some states. The last section then is where you put all this together. These are the rules and the actions, and you might not be able to see that down the bottom there, but I'm not sure even if that helps. But generally speaking, you have sort of three items here. You have a state, a regular expression, and then an action. The regular expression is the thing you're trying to match. The state allows you to use different sets of regular expressions in different places. So if you wanted to have a different way of working with comments, for example, you could recognize the start of a comment, switch into the comment state, match just a small subset of regular expressions, and then swap back to a different state when you're done. And the action then is what you want to do with it. Typically, this is fairly straightforward, and you just want to return the token that you've matched. So here's the regular expression, you match it, it's great, there you are, it's an identifier, and that's what you return back. But wait a minute, regular expressions and parsing, we're always told never to use regular expressions for parsing. What's going on here? It's like regular expressions are not safe for parsing. You don't never ever use regular expressions on HTML, for example. It just won't work, and you're going to have massive security problems. So why am I using regular expressions here? And it's like, don't worry, don't panic, it's not so bad, because we're using regular expressions for lexing. So we're not trying to match big constructs here, we're trying to match keywords, or identifiers, or comments, or and so on. So it's not so bad, don't panic. All right. So this is a Lexa file that I've written. Can you see that? Do you need the font a bit bigger? I'm checking if John's in the back, you can see. All right, so again, we've got then block at the top, some using statements. We've got some directives here, use Unicode, use this namespace, do stuff. And then we create a number of regular expression macros, things like this, where I'm saying, I want to match new line characters, I can match carriage return, line feed, a whole bunch of other Unicode interesting stuff. And go working, here's a slash, here's an asterisk, here's everything that's not an asterisk. And then you can build up things like, well, here's a single line comment, slash slash followed by any number, 0 or more input characters. And then I can use those as my, in my actions. And here are the rules down here. So YY initial is just the default state, so we can ignore all that. I'm matching some, is there a comment one in here somewhere? There we go. Single line comment, there's the regular expression, and there you go, I just return the token, end of line comment, so it's a single line comment. And that's kind of basically it, which is nice. But that then is the whole Lexa for Shade Lab files. So that's cool. But what does it mean? How does it work? So the Lexa generator generates source code for us. So it's going to take that input file and generate me now a C# file, which is off the back of this. All of the rules, which are regular expressions, are converted into a single finite state machine. And this is cool. Because all of the regular expressions are combined and they are matched at the same time. I'm going to say again, that's cool. It's encoded into state transition tables, which means that the lookup is based on the current state and an input character, and that means it's really fast, because it's just a lookup in a table. So, yay, we like this. However, it is not very maintainable. This is the file that gets generated. So, okay, fairly normal, fairly normal. And then all of a sudden we start getting into tables. And tables, and tables, and tables, and tables, and oh, more tables, and then finally get some crazy rules down there. You can't work with this. You can't debug this. So this is the downside to Lexa generators. They are very good in sort of generating what they do. They can generate very efficient code, but it's really hard to debug. So you have to have a lot of tests around it, a lot of input and output tests, and work with it from there. So I mentioned that this whole regular expression thing is very cool. Let's have a look at it. Let's say we've got a regular expression like this, a very simple one. It's an A followed by a B or a C, followed by 0 or more Ds, followed by 1 or more Es. So fairly straightforward regular expression. Everyone got that? Sweet. This is how you write it as a state transition diagram. You start in a state of 0, you can match A, and that's great. We move on to state 1. From state 1, we can match either a B or a C, and that moves us to state 2. At this point, we've got this nice little loop here where we can match either a D or an E. If we match a D, we stay where we are, and we can just keep cycling and match 0 or more Ds. Or we match an E and move on to the next state, at which point we can match more E's. We've already matched 1, so we can match 1 or more, and we've finished. And now we can encode that into a state transition table. So here's our table here. We've got the states down the, as rows, and then the characters which we're going to match as columns. I've got an extra column at the end there, which is other. Just assume this kind of goes on for all the characters that you're able to match. We start at state 0. And let's say we try and match the character B. We look that up, state 0, character B, we get an E, it's an error. We don't have anything for that. We don't have a regular expression to match. So let's try A instead. We've got a match. And we've got this idea of M1 means we match, and now we can move to a new state, and that can move us to state 1, so we go down a row. And we're in state 1. And if we tried to match an A again now, so if somebody had put A, the second time we try and match an A now, we've got an error. So that doesn't work. So let's say we match B. If we match the B, that works. We've got a match. It moves us on to state 2. So we can move down to row 2. If we match D, that'll say it's a match. We can now stay on state in state 2. So we stay on row 2. And if we hit D again, we'd match and we stay at D, and everything's good, and we can keep repeating and keep going for as many Ds as we want. When we hit E, we've got another match, and it's going to move us to state 3. And we're down at the bottom here. If we matched E, then we would stay in state 3, and we'd keep looping and match all of the characters. And then any other character, we've got the A, we're accept. There we are, we've matched it. So just by looking things up in a table, we've been able to match a regular expression. That's cool, right? It's not just me who thinks that's cool. Well, it gets better. Now we can add a second regular expression at the same time. So we've still got our starting state A of 0. If we match A, we'll move on to state 1, and we'll do the same thing we did before. Or we can match a second regular expression, which is 1 or more digits, 0 to 9. So our state transition table diagram, at state 0, we can match the character A, or we can match the digits 0 to 9. If we match 0 to 9, we'll move to a new state, state 4. And from there, we can match 0 to 9 again, and we can keep on looping. And we can shove that into our table as well, because it's basically just adding a new state, a new row along the bottom there, and also new columns for the characters we're going to match. So if we start at state 0, if we match A, we'd move on to state 1, we'd carry on as we just did. But if we had a digit matching 0 to 9, we've got a new match. We're going to match, move to state 4, which is a new row down the bottom here. If we match 0 to 9 again, we stay on in state 4 and keep on looping. Any other character there, we've accepted, and we've matched it there. So now we can match 2 regular expressions at the same time. Relax, we're done with the state transition tables now. So the whole point of this is that the state transition tables are really fast. So it's just looking up, it's just array lookups. It's very easy, very straightforward. But the trade-off is size. So now you need to have a table entry for every character you're going to match, so all the way across in columns, so that if you're in Unicode, that could be really quite a lot, and then for every possible state that you've got. But then if you look at the shader lab file, I think in the end there is about 28 different states. So it's not that bad. It's a known cost, and it's a fixed cost. because you only need to initialize the array once. And you can match everything you need. So if it's Unicode, you've got a column for every character there. You can match new lines, you can match null characters, you can match non-printable characters if you really, really wanted to. So you're working good there. And you can also handle unexpected input there, actually. Sorry, not output. You can handle unexpected input there. If you are matching a character that you're not expecting, you can have a catch-all rule, which is basically saying, here's a bad character token. And it'll just put in a new token into the stream there to say, don't know what that was. All right, so that brings us to parsing. Is everybody all right with lexing so far? Marvellous, yes.
To go back to the case that I was referring to earlier, where
Yes.
it's bad input, will the lexer tell you how far down the matching table it got before it came out?
So
It reports state.
will the lexer report state for where it got to if it gets bad inputs? Generally speaking, no. And this is one of the problems with the maintainability of lexers written like this, because it's very hard to do, because you can't look it up in the state transition tables, because you don't really know what the state transition tables are. There's no really useful debug output that's coming from it. So the short answer is no. But what will usually happen is that you will kind of get one or two bad character tokens in there, and that'll just usually be one character, and then it'll recover, it'll match something else, it'll match something new, or it'll match an identifier. And usually it is something that is matched but duplicated. So if you're talking a C# function, for example, a C# method, where you've got like an open brace, if you typed 3 of those, it would just, that's not an error at the lexer level. The lexer is just going to say, oh, you got 3 open parentheses. It'll be an error at the parser level instead. So generally speaking, the lexer is just going to give you valid tokens unless you give it really weird input, usually binary files. Okay, so parsing then. So this is kind of going up a level, I guess. We've got our stream of tokens. And what does a parser do is it performs the syntactic analysis. So this will verify and match against the syntax of a file. So we know we've got a stream of tokens. This just makes sure that the file is now valid. So I could have a file which is completely open brackets, and the parser will then verify that for us. And again, this is really cheap, or it can be really cheap, because it's just pattern matching on a stream of tokens from the lexer. So this is usually looking at integer values or an object reference comparison, but it can also look at the current token offset and the text as well. So one thing you might want to do, or rather, one example here would be C#, the var keyword. The var keyword is only a keyword used in certain places. Everywhere else it's an identifier. So you can actually create a class called var, which is just going to confuse everybody. Don't do it, but you can if you wanted to. The syntax for a parser is described by a grammar, and a grammar is represented as a hierarchical, as a recursive hierarchy of rules. So the top level is the whole file, and it kind of gradually gets smaller and smaller down to the smaller constructs within the file there. So you compose it down into different structures and finally to matching tokens. So as an example, with my shader file here, to match something like this, or to express that as a grammar, we have some constructs on the left. We have a shader file block. That is a shader keyword, a string literal, a left brace, a properties block, well, in fact, 0 or 1 properties blocks, 0 or 1 tagged blocks, some stuff because it's more than that, and then a closing right brace. And we get to define it recursively. So the properties block is then defined as a block, properties keyword, left brace, I should look at this screen actually. 0 or more properties, which I haven't defined on the screen here, and then a closing brace, and the same with the tags and so on. So recursively we define it in smaller and smaller chunks. Parsing is not solved in the same way that lexing is. There are lots of different ways of doing parsing. So there is no right answer here. There's probably a couple of wrong answers, but it's not solved in the same sort of way as lexing. You can't just immediately go to a default answer. But there are kind of 2 types of parsers, really. you've got a top-down recursive descent parser or a bottom-up recursive ascent parser. And these are the sort of two main ways of working with files and parsing them. And the top-down version is perhaps the more intuitive, and this will match the whole file first. So we say, right, I've got a stream of tokens here, that's going to be a file, and then you kind of could recursively split it into smaller constructs. And so you kind of step into it and you work with it. So as you go along the stream of tokens, you say, okay, this is going to be a whole file. Right, now I'm going to match this construct, and then I'm going to match this, and so on until it gets smaller. Bottom up is perhaps slightly more unintuitive, because you start with the first token, and then you combine that into larger constructs. So you would match something like well, I'll come on to that one. It's a little bit harder to explain, and so I'll show it. With top-down parsing, the easiest way to imagine this is with a C#. Is everyone familiar with C#? Seeing it's a .NET thing? Very good. If you imagine a C# file, the file is split into a chunk of using statements and then one or more namespace blocks. Each namespace block itself is split then into one or more class declarations. Each class declaration is split into one or more properties, fields, methods, and so on declarations. Each method is split into expression statements, and each expression statement, if it's an if, for example, it's got a method body, and you can parse it down, you can narrow it down, you can just sort of iterate through that, and you can see how that would work. And that's how a top-down parser would work. It would match the file, then it would match a usings block, a using statement, and so on, until it got the whole file parsed. Does that kind of make sense? Lovely. And this is kind of pseudocode to sort of explain it. Thinking again about the sort of shader lab grammar that we had before, you'd start with parsing a whole file. The first thing you do there is, right, well, parse me that shader command. And there you would match the keyword, and then you'd parse the rest of it. And parsing the rest of it, you'd kind of match the string literal, match the opening brace, check to see if you've got a properties keyword, because it's 0 or 1. If you do have a properties keyword, go off and parse it. And so on and so on. Until finally you got to the last matching token there of the right brace. And one thing that isn't sort of shown here really is errors. We'll kind of get to that. A bottom-up parser is trickier. It's more awkward. It's also called the shift-reduce algorithm. And the way this works is that you match a token, such as an integer, and you shift it onto a stack of tokens you've already matched. So you could have matched, say, an integer and a plus sign. If you match another integer, you shove that onto a stack, then you look at your stack of current tokens and says, does that look like something I know? And it's like, yes, it's an expression. Okay, I will reduce it down into an expression. You then match your next token and say, perhaps that's a plus and an integer. And it's like, okay, I've got an expression plus integer. I can reduce that down into another expression. And then look again, and perhaps you can reduce it down into, I don't know, a console write line or something. And so you repeat, and as that gets built up, you kind of start at the very small building blocks and work your way up to then having a full file parsed. Similar example there with kind of like a using statement. If you want to build a parser, you don't necessarily have the same sort of way of working like you do with the Alexa generator. Two real ways of doing it. You can hand roll it, you can write it yourself. If you're doing that, then usually you want to write a top-down recursive descent parser, because it's just a mechanical process. It's fairly intuitive, it's fairly easily understandable. Or you can use a Parser Generator. And there are a couple of these. There's yacc, which is yet another compiler, because these were used to build the compilers. And then there's Bison, which is the GNU version of that, because Bison and yacc. It's not my joke, don't laugh. Then there's Antler, which I can never remember what it stands for, but I'm just guessing, antlers. So Bison, maybe. And these are usually bottom-up. When these get generated, they're usually bottom-up because they can use tables in a similar sort of way that the Alexa generator can. But because they're table-driven, then they can be very hard to debug in a similar way that the Alexa can be hard to debug. So I tend to stick with a hand roll type thing. And I can show you. I'm actually going to show you here's an example for a YAML parser. So this one, the shader lab parser I have is somewhat generated. So in fact, let me just. So I've got a grammar. If I get to something interesting. should have opened this file before. One sec. Okay, so I've got a grammar file for my shader lab file, which has kind of got the shader command there. It's got a keyword and then a value, and the value's got a name, a left brace, properties, more blocks which include the tags, and a closing right brace. And this describes then the layout of the file. And we've got an internal tool for ReSharper, which will then generate a whole bunch of code for this. But it's not table driven, it basically generates the whole mechanical top-down recursive descent. And I'm not going to show you that because there's a whole lot of boilerplate around it. Whereas here's one which is, I've written a parser for YAML. Never write a parser for YAML, it's insane. That is handwritten and is a little easier to read there. So for example, we're parsing a document body there. We parse a root block node. In fact, I want to be in the block node. I want to look at that one. And the first thing we do is we try and parse a block node. And it's like, well, okay, I can just recursively look in this. I can try and parse a block node which is made up of either a scalar, so I can then look to see if it starts with a pipe or it starts with a greater than sign, and then parse either a scalar as appropriate there, or I can look to see, where's the collections, if it begins with a minus sign, then I can try and parse a sequence block and so on, and it's a mechanical process. If you recognize a token, go and do this. If you recognize a token, go and do that. And as it gets larger, it builds up the thing you need it to build. But that's not the only way of writing parsers. So that's kind of how I've done it with those kinds of things. There are a couple of other interesting ways of doing it as well. So there's the idea of a parser combinator. And this is a bit of a functional programming kind of thing, where you can build a parser by combining other simpler parsers. So this is very much like LINQ, the language integrated natural query. It's been so long since whatever LINQ stands for. And you know, with the from, the select, and so on, where you get to combine things with methods and so on. It's a similar idea. It's a similar sort of ease of use, but it's also got a similar cost. Calling these functions has an overhead. And so it's not necessarily as performant as a parser which you write yourself. It also, an interesting thing is it combines the lexer and the parser together, because you can have a parser which matches to produce a single token. So you can actually build it up from there. So you could have a parser which said, match me a string, match me a float, match me a whatever. And even though it kind of looks a bit different, it's still just a top-down recursive descent parser. Here's an example of a bit of F#. Don't get scared. It's fairly straightforward. This is from Phil Trelford's blog. If you kind of actually read it from, despite it being a top-down parser, you read it from the bottom up. You've got a P command. So this is the command parser. It's saying match either, parse me forward, parse left, or parse right. So that the pipe symbols and the angle brackets there are OR, so it's either parse forward, left, or right. If you have a look at the definition for forward, that's saying parse me a string of FD or a string of forward, followed by one space, followed by a float, and then do this when you recognize it, and it calls the forward function there. Same with the left, parse the string left or LT, followed by a space, followed by a number, and then if you get it, do this. So it's fairly straightforward, and it's actually really quite nice and readable. And again, you're kind of seeing that I don't have to have a lexer here, I can just parse a string. You can do it in C# as well. There's a tool called Sprach, which kind of puts it into LINQ. I'm not sure I like this syntax, I have to confess. But you can still easily see what's going on there. You can read many whitespace characters, followed by a letter, followed by many letters or digits, followed by whitespace, and followed by, and then sort of put that into a string there, and you can then call this parser to do all that for us. I'm not sure whether the LINQ syntax kind of really helps in that particular case, but you can do it. Interestingly, ReSharper does use this library, but only for during setup. We write our own parsers for pretty much everything else. When's pizza? Is it
9:30?
half past? Right.
We got a
Alright.
quote pass and it's not here, so
Okay, cool. Well, let's crack on then.
I'll pass it.
Okay, so I mentioned earlier that the IDE introduces a whole bunch of interesting constraints, and also everything I've kind of talked about so far, you could look up in a book and it'd be fine. You know, the compiler's book, parser's book will give you this kind of information. There's a bunch of stuff that people don't tell you as well, and how to do this. And when you're writing things, it's like, well, how do I work with this? And it's kind of non-obvious. And so I kind of want to, this is where it kind of becomes a bit more sort of war stories of a bit of advice of things that you kind of don't necessarily think about when you kind of know the theory and how to actually make it work. So the first one is whitespace and comments. So we'd expect this to work. There's our grammar, a shader block. It's a shader keyword, a string literal, left brace, some stuff, and a right brace. And it's like, well, okay, that's what we've got in our actual file. The shader keyword, string literal, left brace, some stuff, and right brace. But that's the actual input we get. And that then sort of lexes down into this beast here with, you know, a shader keyword, new line and white space, string literal, new line, white space, new line, comment, new line, left brace, and so on. And so it doesn't match. So the grammars doesn't match. How do you deal with this? And the answer is fairly straightforward. You actually just filter out the bits which are not important. And so the lex is returning you a stream of tokens, and you just filter out the tokens that are not interesting, that are trivial, that kind of get in the way. You filter out white space, you filter out comments. You can do this very easily. You use a decorator pattern, wrap a lexer, and have a lexer which implements the same interface, but simply swallows the tokens you're not interested in. But that raises the question then, is it safe to lose the white space? And the only answer to that is, well, what are you building? Do you care? And IDEs introduce nice constraints here. So what we want to use this information for when building an IDE is things like code editor features, so syntax highlighting, code folding, and so on, syntax error highlighting, inspections, refactorings, formatting, and so on. Most of those don't really care, but some of them really do care. Formatting cares about white space and content and comments and so on. If you're refactoring, we need to pull the comments where we're moving code and keep it working like that. So an IDE needs to work with both the contents and the structure of the file. So the contents give us the semantic information, but the structure allows us to kind of, it allows us to report where our inspections are showing errors or warnings and so on. It allows us to rewrite and create refactorings. And basically we are mapping the semantics back onto the contents of the file. So it's the map between the two. So in memory, we need to represent the structure of the file when we parse it. And the obvious answer to this really is to use a syntax tree. And inspections can just walk the syntax tree, look for patterns and put highlights in there. Refactorings can just rewrite the tree, and when that gets serialized back out, it's rewriting the file. But it's not necessarily an abstract syntax tree. So this phrase kind of gets bandied around about, it's abstract syntax trees. This is a little bit of a pedantic point, but it's important. An abstract syntax tree is not what we use, because abstract syntax trees are... Stop right there, pizza. I'll finish the sentence. Abstract syntax trees, these two trees are equivalent, for example, here. So the one on the left, which has got brackets to show around a particular expression, that's not needed because the structure of the tree tells us where the brackets are. So these two are equivalent. And it's not that's not what we need. What we really want is a concrete parse tree. And a concrete parse tree has everything in there. It has all the white space, all the comments, all the tokens. So whereas an abstract syntax tree represents an abstract view of the thing you've got, this is the actual sort of concrete thing. This is the text of your file. Very quickly, and I'll just finish this little block. So the upshot is, for my particular use case in an IDE, we need those filtered tokens, so we have to put them back in. So we actually have an extra step in our little pipeline here and a missing tokens inserter, and we have to find the right places and put those tokens back in. So it sounds difficult, it's actually fairly straightforward. You have a second pass after parsing, and you basically just walk everything, compare it, and where there's a gap in the tokens, you just shove some tokens in, and you keep going until there's a gap and you shove it in. It's just a nice mechanical process. You need to keep track of what you've lexed before, so you tend to cache the output of the lexer. But again, that's just going to be an array of integers or object references, so that's fairly straightforward. And yeah, you just shove them back into the tree where there are gaps. Right, okay, so we'll pick back up again where we left off. So we just had a look at some issues where, how do you deal with white space? And the easy way is to sort of strip it out, filter it out, and in my case, I need to shove it back in again afterwards. And that then kind of leads you on to something a little more interesting, is like, what about significant white space? So how do you deal with white space that you can't strip out? How do you parse something like this? F# again. Don't worry what it does. It's not important, but the key thing is like, you've got the for statement there. There's no indication of where the for statement ends other than by indents. The same with the if statement. So how do you deal with that? So in C#, for example, that's fairly easy. You either parse one statement or you parse an open brace and go down to the closing brace. But there are no end of scope markers here. And we've also filtered out the white space, so how do we deal with that? And the answer to this one is really quite interesting, because you actually insert tokens. You insert some zero width tokens. So again, you can have another decorator around your lexer, and this one keeps a track of the white space before it gets filtered. And so it counts the indents and the outdents, or the unindents, depending on whether you think outdent is a word or not. And it will insert sort of invisible tokens into the token stream. So it will indicate where a block starts or ends based on the current indent level. You can also insert a token to sort of indicate when you've got invalid indentation. So perhaps you're, well, for whatever reasons there. One of the key things is that the token is zero width. So it doesn't really affect offsets anywhere. It's got no size in and of itself. It doesn't affect the parse tree. It's just there as a marker. And now the parser can actually match these tokens in the grammar itself. So as part of the grammar, it can say indent, outdent, and so on. There are other sort of interesting problems. And again, F# throws up another fun one here. The two dot and the two dot dot in those two things there is ambiguous. So the two dot is a float. 2.0 is a range operator from 2 to 0. How do you deal with this? Because the original lexer could match 2 dot as a float, and then the 2 dot as int dot dot, but int dot dot is no good because, well, it's messy. And again, you can use this with another decorator around your lexer. And this decorator would recognize when it gets this int dot dot pattern, and when it's asked for a token, return sort of 2 tokens effectively, or rather, sort of on each loop return a different token, and it can return an int token, and the next time it's called return a range operator token. And so you can sort of work around that issue there. Regular expressions don't always work. I'm wandering around again, sorry. I'm making his life harder by moving, this is funny. Regular expressions aren't always good enough at matching things. So for example, ShaderLab supports nested comments. And it's not just that they have to be counted as well. So for example, they've got 2 opening and 2 closing comment things. They've got to match, they've got to work and everything. You can't match that with a regular expression. This is kind of getting back to the whole trying to parse HTML with a regular expression. So you can't match that. So what you have is your lexer has a rule which matches the start of a comment. And then, do you remember way back I was talking about the rules? You can have an action. That action usually just returns back a token. But what the action can do is it can actually just carry on lexing, and it can do it all for you. So then you just walk the characters that are in the stream, counting start, counting end until you're at the end, and then wrap everything up as a token there. So you can actually do some manual things there. And basically the moral is just because it's generated code doesn't mean that you can't extend it, you can't modify it, you can't change it, you can't change some of the behavior there. And it's very easy to fall into the trap of how do I make the lexer generator do that? Like, you don't. You use the escape hatches to put in your own code or wrap it and do your own thing around it. There's another issue as well, which the ShaderLab one threw up, is that some tokens can appear anywhere in the code. So in the ShaderLab file, we've got this idea of preprocessor tokens effectively.
we've got the CG program block down at the bottom there. So the whole CG program block is parsed as a different language, actually, as a CG stuff which talks about GPU and does things. And those can appear pretty much anywhere, and they get then translated into another language as the file is processed. But because they can appear anywhere, we need to deal with them anywhere. And it's like, how do you add that into your grammar and parser when these tokens can just suddenly pop up? There's a similar sort of thing then with C#, obviously, where you've got your hash if false and hash end if and so on, or hash region. They can be absolutely anywhere. They can be inside a block and outside a block, and it's very messy. They're horrible, in fact. And the answer to this one is you parse it twice. You have a stream of tokens. The lexer doesn't care what order things are. It doesn't care where the tokens pop up in that stream. So you parse it twice. The first pass looks for these preprocessor tokens, and it parses those contents, and it feeds that information into another filtering lexer. And when you normally would ask for a token there, it kind of returns you back a block saying, oh, this is preprocessed stuff, don't worry about it. I'll rephrase that, sorry. It doesn't return anything. It says, this is preprocessed stuff, I don't return anything, and it would skip that and then give you back the next significant token. And so then you can just parse normally, because to your parser, it looks like there's nothing there. And then once the parser has finished, you have another step which shoves those missing tokens back in. Or, in my case, when I'm building the tree, it shoves those tokens back in again. And so the final tree includes all those pre-processed nodes, those pre-processed blocks, but my parser hasn't had to worry about them suddenly appearing in the middle of another expression. OK, error handling, or as we like to call it, error handling. This one usually, well, it is more of an art than a science. This one is where you're really not going to find much documentation about how to deal with this. Why do we care about error handling? It's you want to give useful errors to your users. You don't want to basically have a single token missing and then say the rest of the file is invalid. So if you're typing in an IDE, you don't want to have the rest of your file highlighted in red just because you've got a token. You're missing a semicolon in a block. The same with a compiler. If you're compiling, you wouldn't want your compiler to say everything's broken. It would just like to say you're missing a semicolon here. So basically, we need to recover when we've got an error. The other thing to point out is one of the constraints of an IDE. When you are working in an IDE and when you're typing, your code is broken most of the time. You don't write in statements. You don't write in complete code blocks. You write character by character. Most of the time, your code is broken. So there's two kind of things you can do. You can fail fast, or you can try and recover. So what happens when there is an error? In my particular case with an IDE, well, the parser simply adds an error element into the tree. Into the tree that I'm building, I have a block which just sort of says there's a syntax error right here. And that error spans what's been parsed so far. It starts at the beginning and at the end. And when we want to highlight that in the editor, we just find that error element in the tree, and we put a squiggly underline from the beginning to the end of that block, and that's it. And yeah, the span, yeah, we'll recover that. So how do we find an error? The start is obvious because we've just hit something we don't recognize. So bang, there it is. Where the error stops is the tricky bit. Because an off by one token, so if everything's just shunted along one, that could affect the rest of the file. So we have to try and recover. How is the tricky thing? And there are kind of three main ways of doing this, really. There's panic mode, which is a great way of describing it. There's token insertion and removal, or substitution, and there's actually encoding the rules into your grammar as well. So panic mode is basically just eating all the tokens until you find something you recognize. So here's an example from shader lab syntax there. We've got the second property there, prop name. It's expecting an open bracket there. It doesn't. It finds an identifier. So it's like, panic. And it just keeps on going until it finds another identifier, the underscore recovered. And it says, OK, I found an identifier. That's going to be the start of my next rule. On you go. So panic mode. It's recovered. So that's not bad. That's a reasonable sort of recovery there, and a reasonable sort of error to apply. But using the same algorithm effectively, on the second example, it fails completely, and it gives us a weird error. So again, it's the second error. We've got it hits the identifier syntax error. It's expecting an open bracket. I'm sorry, I know that's a bit low on there. So it's expecting an open bracket. It finds the identifier, which is syntax error. So that's an error. So right, I'm going to eat tokens until I get to the next identifier. And immediately there's another identifier. It says, great, here's the start of a new token, of a new property, a new line, effectively. And it tries to parse that. And then instead of finding another open bracket, it finds an equal sign and goes, oh, no, I don't know what to do now here. And it's another error. And so all of a sudden, I've kind of got two syntax errors here when that's not really what's happened. So my error handling is a bit weird in this case. A better way of working is to do something like token insertion or removal. So in this example here, we're missing a closing bracket. So we're expecting a right parenthesis, and we've got the equals character instead. So what we do for this algorithm is we assume that the right parenthesis is missing. So effectively, we skip it. We say, I'm expecting right parenthesis. I didn't get that. Let's pretend I did. Now I'm looking for an equal sign. Ah, I got it. I can recover, and I can carry on. And so now I've got a very localized error, and it's a really good way of fixing things up. But that doesn't always work. So if I've got an extra token, so I've got, say, two closed brackets there, my token insertion fails because I can't insert something else because it says, oh, I've got closing bracket, I was expecting equals. If I insert an equals, does everything work out okay? No, it doesn't, because I've still got this weird closing bracket which I wasn't expecting. So then it can do an alternative and says, well, fine, I will skip this one. Let's say I've got an extra token. I'll ignore this one. I'll mark this one as an error. And I'll look at the next token. The next token is an equals sign. It's like, brilliant, synced back up again, and we can carry on and we can parse on. And so by either doing inserting or removing or also substituting, we can then sort of have a very good way of working, recovering there as well. Another way of working, though, is to assume that your code is going to be broken, and you actually encode it into the grammar. So an example here is an empty block, which is just supposed to be a left brace followed by a right brace with nothing else inside it. And it's like, no, I know what people are like. They're going to put something in there. And so you assume something's going to be in there, and so you encode like this error element, which eats anything until it gets to a right brace. And there we go. We sort of encode it directly into the rules, and the grammar anticipates where there is likely to be an error. All right, last couple of things then. Another big problem for an IDE is incremental reparsing. So if you change your file there, you don't want to parse the entire file on every change. You only want to reparse the smallest subtree that encloses the change. So basically, you walk up the tree where the change is, find the block which encloses that change. So if you are in C#, that'd be like, walk up to a for statement or to a method body or a class or whatever, and just parse that change there. You want to do the same with lexing as well. So you don't want to have to relex from the very beginning until the end, but you want to be able to just relex the block that's changed. And this is actually easier than it sounds. If we cache the lexer output from when you do that, and again, that's just going to be an array of integers, then you can then use that to resync everything back up. You can find where your current change is. You can walk backwards to find, say, the open brace, walk forwards to find the closing brace, and then sync up following on from that. So again, it's just a mechanical process to do that. Really cool thing, which you can do with an IDE, once you're parsing and doing stuff then, is composable languages. So you can have things like an injected language. So with the shader lab, for example, that CG program block, that's a different language in there. And so when I'm parsing it for shader lab, I just have a big sort of opaque block of CG block, basically. But then I can inject a language, and I can say, well, put another parser inside that block and parse that and build a new tree based purely on that code there. We can do a similar sort of thing there in ReSharper with things like syntax highlighting regular expressions in a string literal, which is cool. And that can then build features on top of that and give you code completion and syntax highlighting and error highlighting inside string literals. You can also do inherited languages. So TypeScript is a superset of JavaScript. And so you could then have a parser which is TypeScript, which then has appropriate sort of template methods which you can inherit and override to parse TypeScript. So you can extend a parser like that. Another option you've got then is also nested languages. So if you had Razor, for example, Razor files are HTML, C#, JavaScript, and CSS all in a single file. And it's like, you can't write a single parser which will deal with all of that. You have to basically switch between parsers and switch between lexes to get at that. So that's fun, and it's cool. Which brings me back to the final question there. So how do you parse a file? The simple answer is don't. Don't do it. It all gets too much and everything. Stick with the JSON files, stick with the XML files, and unless you have a particular reason for getting at the structure of the file or for working with particular domain-specific languages, don't. Stick with that. So finally then, last couple of links. All of the Unity stuff is open source. ReSharper Unity is the GitHub link for the Unity support inside ReSharper and inside Rider. That's got the parser for the ShaderLab stuff. It's actually got several parsers in there now, actually. It's got a ShaderLab file. It's got some JSON-specific stuff, and it's also got the YAML parser. The YAML parser is also split off in a separate repository, ReSharper YAML, and there's a lot of fun and games going on inside those. The YAML one especially has a lot of interesting things going on with even more constraints because the YAML files inside Unity are stupid big files. They can be 100 megabyte files, 200 megabyte files, and usually with ReSharper we have a limit of about 2 megabytes. So this kind of hurts sometimes. There's also a couple of links there for generating error recovering parsers because those are tricky. And finally, yes, the last thing there is the ANTL 4 reference book by Terence Parr, which is really good. And so that's it then for how to parse a file.